Okay, since we've finished our experiments with our output transformers and we know what they are and kind of have them measured up, I'm getting them mounted into the chassis here, and I stuck a couple of grommets in there, and the unit comes with grommets, so you want to make sure you put those in there because of course your B plus voltages are going to be present on these wires and you don't want them to be in those holes without them. I have added the speaker terminals, and the reason I'm doing that is so that I don't have these wires flopping around in me while we're working in the chassis. I'm going to go ahead and attach them, at least get them temporarily attached, and then we'll cut them to length later on a little closer and get them done. I put all but the last one in because invariably if I install these, someone will comment and say, hey, you didn't show me how these things install, because they can be a little bit confusing, you know, possibly, I don't know. But these ones, the way they work is, first thing I do is I remove the outer knurled nut off of the outside. I then take the two nuts off of the terminal end. And then you have to watch, there's a lock washer and the actual terminal itself. And then this little lead-through grommet actually splits apart. Let's see if I can get my fingernails or lack thereof in there to take it apart. And you see that pops apart like that. So this part goes into the hole like that. And this part, you can see there's a curved end that faces out. And we put that down in here. And I don't know if the camera's going to see this or not. Yeah, we got it. And this takes a lot longer on the camera than it does off camera. And then you put the terminal, lock washer, and one nut on. And you just want to kind of spin it down till it seats onto the terminal. Now this is kind of a two-handed thing, and it can be a little tricky, but what I do is, you can see I'm holding with this finger, I'm holding the terminal. I'm going to kind of hold it out kind of at an angle like that. And then I'm also going to take a screwdriver or something that'll fit down in here, an Allen wrench or something, and I want to face this hole. This is where the speaker wire is going to go in when you tighten that down. So I'm going to face this downward like this. Some people also like to face them at a little bit of an angle. It's totally up to you how you like it. And while you're holding that with your thumb and holding this with your forefinger, I will go ahead with a little ratchet and a little socket, and I will tighten this down. And you have to watch. If you over tighten it, they'll snap right off. So you just kind of should feel it getting a little bit not as spongy. And you stop right there. And it should be, you can still move it a little bit, but it shouldn't be easy to move. And then you take the second lock nut and put it on top, and just kind of, you're just going to jam it against the other nut while you're still holding everything. And you don't have to jam it real tight, just enough to hold it. And that'll keep that nut from coming off. And then you put the knurled nut back on, and we're done. Now, a word of caution with these. There are a lot of cheap ones floating around out there, especially, you know, on the normal haunts. And they look like they're really good and everything, but what I just did there, tightening that down with this, some of those ones are so cheap that as soon as you try to snug this to where it doesn't want to slide anymore, that bolt back there just snaps right off. They're garbage. Don't get frustrated. That's just the way they are, and throw them away and buy new ones because you just can't tighten them. So these ones, luckily, I found are relative. They didn't look like they were going to be good, and they looked like they were going to be the kind that snapped off, but they weren't. You can see I tightened them relatively tight, and they held. And really, that's the difference between, you know, you can buy a whole bag of these, you know, 10 or 12 of them, you know, for a few dollars online. If you buy good quality ones of these, they can be anywhere from a couple of dollars each, clear up to $20 or $30 each. And some of the audiophile grade ones, I mean, you can get into crazy money. I would never do that, but the ones that are a couple dollars a piece, especially companies like Switchcraft and so forth, those are really high quality. You can really tighten them down well. The plating doesn't wear off. They have actual copper underneath them instead of some kind of a pot metal that they use in some of these. They're just, the fit and finish are a lot better. So that's up to you. That would be an upgrade you could do to these amps if you wanted to use better terminals. These are pretty standardized sizes, so that's up to you. But anyway, these are mounted up, and we're going to connect the wires. In this part, we are going to focus on the output section of the amplifier. Before we do that, I just wanted to go over a couple of things from the previous videos. Namely, one thing that I didn't mention is in the output transformer, which was the last video we did. We talked about a push-pull transformer, but we also measured the impedance ratio on a single-ended transformer. There's just one little note I want to leave when we're dealing with a single-ended transformer. That's a transformer that does not have a center tap on the primary, where you only have your B plus going into one end, and then you have your output tube, the anode of your single output tube going to the other end. Those transformers do have a difference from these other than the center tap. And what that is they actually have an air gap in the core. And that air gap is to allow the transformer to be unbalanced magnetically. These transformers right here, we're going to get into this in this video, when both of these tubes are biased and turned on, they conduct equally in equal and opposite directions. So if you look at the current path, here's your B plus coming into the center tap. So what's going to happen here is current is going to flow up through this, and using conventional current flow, that is. Current is going to flow up through this half of the winding, down through the anode, cathode, and make its way to ground. On this one, current is going to flow this direction, which is an opposite direction, through this tube and to ground. So you have equal and opposite current flows in this coil. So what that's going to do is that's going to cause the magnetic field to cancel itself out. So your magnetic field at idle is going to be zero. There will be no magnetic field there. Whereas with a single-ended transformer, all the current flows in one direction. So you would have your B plus, current would be flowing here through this tube and to ground. So this would have a DC current flowing in one direction all the time, which would magnetize that core. And that could cause what's called core memory, in which it basically takes that iron core, that steel core, and turns it into a magnet. And even if you do that long enough, even after you remove the current from this transformer, and I can see my camera's acting up today, keeps zooming in. I don't know why it does that. This does this randomly once every so many videos. But anyway, this will cause the current to flow in one direction. It will magnetize the core, and the core will no longer be magnetically neutral when you take the voltage away. It'll turn into a magnet itself. And of course, when current has to flow the opposite direction, or the magnetic field has to collapse, that magnetized field will oppose that. So it can cause problems. So anyway, they put that air gap in there in the core so that the core can't saturate or can't magnetize and get that core memory. So that's just a difference. That's why you really can't use one of these transformers as a single-ended transformer. Now, I don't know why in the heck let me see if I can stop this from doing I had one other video a while back that this camera did this. I'm just sitting here, and if you just sit here, you'll see the zoom will just slowly start zooming in on its own. I don't know why it does that. And then after a while, it just stops doing that. Anyway, weird. So anyway, I just wanted to talk about that for a second. Another thing I want to talk about is these pi networks. I'm going to do something and kind of redraw this pi network a little bit. And what I mean by that is, if you notice, we come out of our rectifier, we go through our first capacitor. Then we go through this dropping resistor, or this pi network resistor, and into another capacitor. From there, it comes out, and we'll ignore this branch for a second. It goes through another resistor, so you have capacitor, resistor, and then another capacitor. Then you have another resistor and another capacitor. So notice you have capacitor, resistor, capacitor, resistor, capacitor, resistor, capacitor. And that's how these networks work. And this can be a little bit confusing. Now, this particular circuit is used in radio a lot too. And it's part of a resonant circuit, but that's not really what we're doing with this. We're using this as a filter and as a dropping network. So let's redraw this to see what another way to look at this circuit. Okay, here is our rectifier. Here is our 330 microfarad capacitors, right? It's the same thing electronically, but we just drew the capacitors in a little different direction so that they look a little bit different to us. So what we can see here, and you can see it's the same thing, right? Looking down here as being drawn this way. But if we look at it this way, we have two capacitors that are back-to-back connected like this. So this actually will act as a non-polarized capacitor in a way. But we're center tapped to ground. And if you notice, these capacitors are going across that dropping resistor. And then here is your first load. We'll call that RL1. And that would represent these output tubes here. So this will be your output section. And then this will be your driver and preamp sections. Each one has to have a lower voltage. So if you look at it this way, from here to here is a voltage divider. And as long as there's pure DC, in other words, there's no changing DC current here or voltage, these capacitors will just kind of stay out of the way. They won't do anything. They'll have no influence. And the current is just going to flow through this resistor and divide with this and divide with this node here. So this would act as like its own load. So you'd put these two loads in parallel and they would divide with this. And the same thing over here. These capacitors, once again, are not going to, as long as there's no variance in the voltage or the current, there's no ripple. If this is pure DC, then again, these capacitors are not going to influence anything. They're just going to charge up and then just stay there. And current's going to flow through this resistor, and again, it's going to divide with this part of the circuit. So you can see it's a voltage divider circuit, and that's really what these pi networks in your power supply are doing. Now, in the event that the voltage tries to change, like you have influence of this ripple here that we were looking at, then these capacitors will act to oppose that ripple. So it serves dual purpose. But really what the main reason we're using this in this particular application is to divide the voltage. And so this is a voltage dropping circuit. So from here to here you're going, so you may have, what's it say? We have 278 volts here, right? And then when it divides between here and here through this 3.6K, they're saying that it's somewhere around 172 volts after it gets up through here. So you could see that it drops a lot of voltage, and we can actually measure all of this once this is all assembled and see the voltage drops. But that's really what these pi networks are doing. Just wanted to run over that with you real quick. Okay, let's start out by determining what type of output section we have in this amplifier. Now the first thing we notice is that there are two tubes and there is a split primary on the transformer. So you have your B plus coming into the red lead here in the center, and then you have one tube on this end and one tube on this end, and this indicates that it's a push-pull type amplifier. What is push-pull? Well, push-pull means if you have let me get a little card here. If you have a signal, okay, we're just going to use basic sine wave, right? When we go to amplify this through this section, what's going to happen is this upper tube is going to handle the upper portion of the waveform, or the positive going half cycle. So we'll call this the blue section. And then this bottom tube is going to take the negative going half cycle, and we're going to call that, since that's the yellow wire, we're going to call that the yellow section. So each tube only has to handle half of the waveform, meaning that both tubes together will actually double the signal from what a single-ended amplifier would be. Now, a single-ended amplifier, you would only have one tube. It would be connected up here, and this red lead, this B plus, would be connected down here, and there would be no center tap. And what would happen is the amplifier would have to be biased in such a way that the one tube handles both half cycles. And as you could imagine, the only way to do that would be to bias this thing about halfway at its maximum signal level. And so what that's going to do is that's going to limit the amplitude of that. So that type of output section is going to be about half the amount of power or less than what this one does. We call that single-ended. Now that a lot of people get confused with single-ended versus class A, class B, and class AB and all that. But the truth of the matter is you'd never want to do it, but you can actually bias a single-ended amplifier as class AB, or as class B, or as class C. The class of the amplifier has nothing to do whether it's push-pull or single-ended, and it has everything to do with where you set the operating point of the output section. So I hope you guys will understand that by the end of this video. What we're talking about when we talk about single-ended versus push-pull is, in a single-ended you have one side handling both half cycles. In push-pull you have two separate sides, the upper half taking care of the positive half going cycle and the bottom half taking the negative going half cycle. So that's what single-ended versus push-pull means. But when we're talking about class A, A and B and AB and so forth, that's what we're talking about, is how we're biasing this, how far we're turning this thing on at idle, and how far that signal moves when you're applying a signal to it. So when you drive an input in there, will this tube ever turn off, for instance? So if this tube turns off while this one is still on, then that would be class AB. If both tubes stay on somewhat all the way through 360 degrees of this waveform, that's going to be class A. And then class B is where both of them will turn off, or where in a single-ended the tube will turn completely off and then turn completely on. Okay? So really A and AB are the two that you're going to see the most in an audio amplifier. Class B and Class C have to do with like radio circuits and transmitter circuits, and it's not practical because they would give you incredible amounts of distortion. So we're not even going to talk about those. Now, sometimes you'll see a little number after it. A1, AB1, A2, AB2. What those numbers have to do with is they signify how you're driving the tube. So for instance, if the tube is a class AB1, that means that at full signal or at zero signal, okay, the grid will never swing positive. The furthest that this grid can go would be to 0 volts. There's always going to be a negative voltage. In other words, in a class AB1 or even in a class A1 amplifier, all the way through the entire waveform, when you're driving a signal into the grid will never go positive in voltage with respect to the cathode. If that makes sense. So if you take a meter and you measure from your cathode to your grid, the voltage will never go to a positive voltage. In fact, it will never go past 0 volts. It will either be 0 volts or a negative voltage all the time, all the way through this waveform. When we talk about class AB2 or class A2, because yes, there is even a class A2, you could bias an amplifier. Again, it's not very common, but you can do it. What that means is if you put your meter between your cathode and your grid, sometime during this signal, the grid will actually go beyond 0 volts. It'll actually go into positive voltage. So you'll actually begin drawing grid current through the circuit. And there are designs where you actually do that, but it is not very common, and you don't often very often see that. In this particular case, the way this thing is configured, it is a class AB1. Now, how do we know that? Well, first of all, if we go through and we do kind of the math on all this, how they have this biased. This is a cathode bias. We'll talk about that in a minute. The amplifier is not going to be set at halfway through its operating point. It is actually set below that somewhat. And what's going to happen is, as this amplifier, as you drive a signal into here, from here, what's going to happen is, for instance, during this positive going half cycle, this tube will actually turn on more and more and more. And you'll get more and more signal through this side of the amplifier. At the same time, this one is going to start conducting less and less. It's going to start turning off. So the voltage shift is going to kind of move up here. Then it's going to move back down here. At some point in time, before this reaches its peak up here, this tube here will turn off. It will be completely at zero grid, or it'll be all the way at maximum negative voltage, and it will be in total cutoff, meaning that the tube is no longer conducting at all. It's just turned off. And this one will have the entire load, the entire current, that whole idle current, that whole current will be flowing through this tube. This one will have nothing. And then as you come back down, this guy will turn right. This one will begin to turn back on. And this one will begin to come back down until finally, when they reach their center point here, they'll both be conducting equally. And then as we start to swing negative, then this tube is going to begin conducting more and more. This one's going to conduct less and less. And as we get close to this negative peak down here, this tube will turn completely off. This one will be handling the entire load by itself. Now remember, throughout all of this, the current is pretty much staying the same here. It's just the current that's being shared between the tubes is going to move between this one and this one, if that makes sense. Because as these tubes turn on and off more, the voltage drop here is going to change, which is going to put more voltage drop here, and they're going to equal out. So what's going to happen is that's how Class AB works. If this were a Class A amplifier, what would happen is as you start going positive, this would start taking more of the load, this would start taking less of the load, until finally you get all the way up here. This tube is still turned on. This one is handling more of the load, this one's handling less of the load, but they're both still on. And then as it starts to go back down to here, this one will start to have less of a load, this one will have more of a load, until you get to this center point. They're both equal again. Then when we go negative, this will handle more of the load, this will handle less of the load, and then eventually when we get to the peak, this one will still be turned on a little bit. This one will be turned on fully. So they, at no point in time through here will either one of these go to zero conducting, if that makes sense. That's the difference between Class A and Class AB. All right, so to sum it up, Class A, these tubes never are in a situation where they both turn off. In Class AB, these will be in a condition when they're at their peaks where one tube will be off and the other one will be on and be handling the entire load, if that makes sense. And you can kind of move these numbers around. So you can be in Class AB and you can set it so that it's closer to the peak before this one turns totally off, or further away from it before it turns totally off. You have a little bit of latitude, and some of that has to do with how you set your biasing and so forth. So this stuff's kind of tricky, and I'll be the first to admit, when it comes to drawing the load lines for this in an output section, it's a lot more complicated than drawing a load line for your driver section. These are driving into a resistive load, whereas your output section is driving into a reactive load. Remember, we called this an 8K plate to plate. Well, that's a reactive load, and with changes in frequency and so forth, that load is going to move around, and this all changes. So that load line is hard to calculate. At least for me it is. Let's take a closer look at just the output section of the amplifier. It's really pretty simple when you look at it. You have a couple of resistors here that you normally don't see in most amplifiers. These were added in this kit, and I kept them in here because I think they're really cool. They're only a 10 ohm resistor, so they have very little influence over this, the anode circuit. But what it allows you to do is, number one, these resistors act as kind of like a fuse. If you have a really hard short somewhere, this fuse will pop open before your tube will get damaged, hopefully. The other thing it allows you to do is you can put your voltmeter across this resistor, and you can measure, and 10 millivolts would equal 1 milliamp of current flowing through the anode. So this is a nice, easy place to check your anode current. Now you can also do that by checking the resistance of the winding and calculating it that way, and we've done videos on how to do that. But this is a really nice place to test. Now the same thing goes for these screen grid resistors. Since this is running in pentode mode and not triode mode, what's pentode mode versus triode mode, you might ask? Well, this screen grid actually has an influence over how this tube conducts, and it becomes much more efficient, and it's able to have a lot more output power if you put this screen grid in here and you set it to a voltage that's a little bit lower than your anode. So for instance, this will be somewhere maybe around 250 volts. And if you notice, the anode is at 275 volts. So that's what these little dropping resistors do. And by doing that, you're going to increase the amount of gain of this tube, and you're going to get a lot more output. The trade-off is that will add distortion to your signal. So you have to use negative feedback, which I'm not showing on this simplified diagram, to counteract that feedback, or I mean that distortion. Now, in a pentode tube, you actually have another grid that they're not showing in here, and I'll just kind of give you a little drawing. And they kind of make it look like this, because this is called a beam tetrode or a beam pentode. These are the beams. This is your fifth element of the pentode, and it's connected directly to the cathode down here. And that's called a suppressor grid, and that actually helps take some of the, they call it the anode kink, and I don't want to really get into that right now, but essentially it helps the tube to conduct better, and it helps reduce the distortion that you get from this screen grid up here. So the screen grid allows you to get more gain and more power out of the tube, and the suppressor grid allows you to reduce a little bit of the distortion, and the rest of it you can get rid of with the negative feedback. But in order for this grid to do its job, it has to be at a lower voltage than the anode, and the set point of that voltage will affect the efficiency of the tube. Now, when you run these tubes in what's called triode mode, and that is a valid thing. As a matter of fact, some of the fancier amplifiers will have a switch where you can switch between triode and pentode mode. What they do is they take this grid and they tie it right up here. So they kind of just directly tie it right to there. And that essentially deactivates this screen grid. And then the tube acts like a triode tube where you have a cathode and anode and a control grid. And this thing acts like it's not even there. So that's called triode mode, and your output will be reduced substantially. So this amplifier that's going to be 10 or 12 watts right now, if you ran it in triode mode, it probably would only be about 8 watts or so on a good day. So that's, everything has a trade-off in vacuum tubes, and you're going to find that out the more we talk about this. Now, all these little numbers I wrote in here, where did I get these numbers? Okay. Well, you can look these things up in the tube charts. So there are charts that give you the recommended settings and how the tube will typically, and I say that very stressfully, typically react with a certain voltage and current on it. And in those tube charts, you can actually look these things up. Now, here's the problem. The tube that we're using is a 6P1P. All right, I don't know why they left the P off of there, but, and that would be this. And this is a Russian type tube. They're made in Russia and in China, and they're called 6P1Ps. Those funny looking ends are actually translate to the letter P in English. And there's very limited data for these tubes. So this is all you get. You get the maximum ratings and you get a basic emissions chart, and that's it. You don't really get much information on these tubes. So when you don't have all the tube data, it makes it very difficult to calculate things. But luckily for us, this tube is electrically the same as several other more common tubes. And when I say electrically the same, what I mean is that they have the same elements inside that react to voltage and current and so forth the same way. The biasing is the same and everything, but the pins are connected differently. So pin 1, 2, 3, they are not connected the same in these other similar tubes, nor are they in the same type of package. So this is a 9-pin package. This is a 9-pin tube. I'll put some pictures of these tubes up on the screen as I'm talking. And electrically, though, it is the same inside as a 6AQ5, which is a very common tube. It's also the same electrically as a 6V6, and it's also electrically the same as an EL90. Now, these two tubes, 6AQ5 and 6V6, these are tubes that were very common here in the United States. An EL90 was a European type tube, very common in Europe, of course. And all of these, although they're made at different parts of the world, They are made to the same specifications, but they were just had different pinouts and different packages. So for instance, a 6AQ5 is a miniature 7-pin package. This is a 9-pin miniature package. 6V6, on the other hand, is an 8-pin octal, which is the big tubes with the big plastic bases. So they're in a different package altogether. And then the EL90 is in the same package as a 6P1P. It's a 9-pin tube, but a completely different pinout that's incompatible with this. So even though these tubes are all the same electrically, they're all different wiring-wise. So you can't just plug one of these in place of this. You'd have to change the tube socket, and you'd have to change the wiring of the tube socket. Other than that, they will work. Now, why am I telling you all of this? Well, there's a heck of a lot more data sheet information for these two tubes than there is for this one or this one. And so therefore, we can actually download and print out these data sheets and get the information we need from them. Now, what you're going to find is a 6AQ5. When you start looking up the 6AQ5 tube, and I think I was cutting you off here for a while, I apologize. You're going to find that it will give you all the information if you're building a Class A amplifier, but not Class AB. Whereas, and some of them will have a Class AB, but they're only at lower voltages than our amplifier is operating. Whereas if you look at the data sheet for a 6V6, it actually has voltage settings very similar to our amplifier that we have right here. Okay, here is a section, and I just expanded it, but it's basically from the data sheet for a 6V6 tube. And it shows, if we go back here, remember we're putting about 275 volts on the anode here according to the instructions. And it may even be a little higher than this, because remember our mains voltage is a little higher than 110 volts. And lo and behold, 285 volts. They actually have, for Class AB1, values for 2 tubes for your push-pull. And it shows if you have a plate voltage of 285, but they actually have a screen voltage of 285. So this is Class AB1. However, this is running the tube in triode mode. So these numbers are not going to be perfect, especially when it comes to your grid voltage. This is going to be a little bit different from this. When you change this and drop it down to 250 volts, what you're going to find is that this is probably going to need to be a little bit lower to get this to work like that. Or a little bit higher maybe. It just depends. So all of this is going to, but at least this is going to get us in the ballpark of where we should be. And you're going to see, if you go back and notice effective load resistance that they recommend for your transformer is 8,000 ohms. Whereas if you're only putting 250 volts on the anode, it's a 10K transformer. And again, we can play with these numbers too. I could lower this a little bit more, but then it's going to affect how I have to set this and how I set this. So all of these things kind of interact with one another. All right, let's go back to here. Kind of hold them side by side. So if you look right here, you can see we have 275 volts, which is a little bit lower than this 285. It's 10 volts less. And it says that the operating point of this amplifier, if you're using 285 volts in triode mode, I should have somewhere around minus 19 volts. And I put here that this is probably going to be sitting between minus 16 and minus 20. The other thing is, this is probably for the design of a fixed bias tube. Now, I told you earlier I'd get into what's fixed bias and what's a cathode bias. This amp uses what's called a cathode bias, and that means we need negative voltage on this grid to control how this tube is conducting. If this were 0 volts or positive voltage, this thing would crank up and it would pretty much overload and red plate and burn up. So you always have to keep a negative voltage on this grid to keep this tube from overconducting. And there's 2 ways to get that negative voltage. We can force a negative voltage on here by taking another power supply, a negative power supply, and attaching it to here and fixing it at that negative voltage. The other thing we could do is trick the tube into thinking that this grid is at a negative voltage. And the way we do that is we raise the cathode above ground. So when you measure from here to ground, you will get a positive voltage. But when you measure from here to here, it will show up as a negative voltage. So the higher you bring this thing up, the more negative this grid will become. So really, by adjusting the resistance of this cathode resistor between ground and cathode, we can set this to any negative voltage that we want. And the beauty of using a cathode bias like this is it's kind of self-regulating, because if you raise the voltage up here on the anode, it's going to also raise the voltage drop across this resistor, which is going to raise this negative, or going to make this negative voltage more negative, which is going to regulate the current down a little bit. So it's a little bit self-regulating. Whereas if you have a fixed bias, this cathode is going to be tied directly to ground. So there is no resistor to spread that voltage across. So if this voltage goes up and you don't change this, the current through this tube, because this is tied directly to ground, is going to go up, unless you manually adjust that negative voltage. So there's pros and cons to fixed bias versus cathode bias. I'm not going to get into that in this video because it just would take too long to go over all that. But this is a cathode bias circuit. Now, because of that, this negative voltage is probably going to be a little bit different than it would be if you were going to set it to fixed bias. So again, all that talk I just did is just to tell you that don't be surprised if it's not minus 19 volts. And you can see that's why I gave it about a 4 volt swing. It can be anywhere in there. And really all we care about is we want 70 millivolts of current through this tube, maximum. Or I should say 70 millivolts both together. So I want 35 millivolts here and 35 millivolts here, and the two combined go through this one resistor, so you should have a total of 70 millivolts here. And in order to get 70 millivolts, since this is 270 ohms, 1 volt is going to equal 3.7 milliamps, and therefore somewhere between 16.5 and 18.5 volts, this will be right around that current that we're happy with. Okay, if this voltage is a little bit lower, it's going to be biased a little cooler, so the tubes run a little cooler, but you have a little less output power. If you run it up closer to this 18.5 or 19 volt level, then these tubes will be running a little bit hot. You'll have a little more output power, but the tubes are going to run a little hotter and they'll wear out a little sooner. So again, everything's a trade-off. So the bottom line, it's so much easier to just build this circuit and test it and show you how it works than it is to sit here and talk theory and math formulas and things. So let's build the amplifier and let's test it and let's see what we get. All right, as you can see, I built up part of this amplifier, and all I did so far is I built the one channel. Okay, so this will be the left channel. I left the right channel unbuilt, and we're going to build that one in this video. We're going to do a little solder and chat. Some of you really like that, some of you don't. We'll do it at the end of the video, so those of you who don't want to see me solder a bunch of parts on the terminals, you can cut it off there. So I built this part up. This is the power supply back here. You can see these capacitors. So again, we're coming out of here, which is this one here, and we saw this in our power supply video, right? And then it comes from there, goes off to this 1K 2-watt resistor, which is right here, and that's what's feeding these two 300 ohm resistors, one here and one here, to feed into the screen grids, pin 2. So you see that. And then it also branches this direction and goes to this 3.6K resistor, which is this one here. There's 3.6K, goes to this terminal, and that terminal is going to feed over up to here. So we're not even going to use these ones yet. And then from there, it goes through a 20K into another 22 microfarad capacitor, just like that. And that's going to feed this part of the driver tube. And none of this has been wired yet. We only wired it from this part back. This is the beauty of these capacitor coupled amplifiers. You can actually build one stage at a time and test them individually. And even when we build this part back here, I can remove these two tubes from the circuit altogether and just power this section up and test it right here and see how it's going to drive this. Now that's going to affect our power supply, because once again, this is an unregulated supply, and by not having a heavy load here of these output tubes, this voltage will be higher, which will be higher here as well. We'll get into that later. So anyway, this is what we have now. And you can see here's our 0.1 microfarad capacitors. It's right here. Here is our what do we call these? Grid leak resistors, whatever you want to call them. And they're going to ground, and they're 470K. You can see them right there going to ground, 470K and 470K under here. We have our cathode bias resistor, that's 270 ohms, that's right here. And then we have, I have a 470, actually I had a 500 microfarad, same difference. So 500 microfarads at 50 volts. And I've just put it over here, and you can see this ties from here to here. We'll see how it assembles later on when we do the other channel. But anyway, it's all wired up. So what we're going to do is we're going to start out, first of all, by putting our meter from here to here. So we're going to measure across this resistor. If this exceeds 19 volts, we know that there is more than 70 milliamps flowing through these two tubes combined, and we're exceeding our idle current, and we're going to have to shut things down relatively quickly. Now, the other thing is we only have one channel built, and as we only have one channel built, we're not putting the full load on the power supply, so this voltage is going to float a little bit high. Now, to counteract that, what I've done is down here I have this connected up to my dim bulb tester. So I actually have a current limiting light bulb in here that's going to drop this voltage down, which is going to limit this a little bit. It's going to kind of offset not having two amplifiers built. It's also going to act as a current limiter if something's shorted. We don't know. I mean, I built this, I haven't powered it up. If something's shorted, I did something wrong, this bulb will get really bright, but it won't fry, hopefully won't fry my amplifier. So there we go. Now with that all in mind, let's put this here. Let's connect. Let's see, we want to go to ground. This just goes to ground right here. So I'm just going to use this ground terminal over here. We'll just connect it. And we're going to connect this part of the cathode resistor right here. So we now have the meter connected directly across here. I have the two tubes plugged in on the bottom. Let's turn this up to DC volts. Let's get a plug. Let's see here. And I have the dim bulb turned on. I do, yes. So it's, and I have the switch turned off. Power switch is off. Let's plug this in. Hopefully nothing will go boom. All right, the moment of truth. Let's flip the switch. All right, the dim bulb lit up and then went dim. So that means the capacitor's charged. And now the tubes are warming up. Let's see if this thing starts to conduct. And it is. Okay. So it looks like it's biasing somewhere around 16 volts. So let's do a little bit of quick math here. That's still climbing up as the tube warms up. But 16, let's say 16.5. 16.5 times 3.7 milliamps per volt. We have 61 milliamps we're idling at right now, and we want around 70, so that's good. And the dim bulb is actually, the light bulb current limiter is actually doing its job. So that means a couple of good things. Number one, it means that we're right where we need to be, and it's where we predicted. Number two, it means that the circuit is working. If either one of the tubes was not working correctly, this wouldn't be doing this. So that looks good. Now, what I want to do is I'm going to remove this very carefully and remove this very carefully. And now what I want to do is I want to measure my grid, which is going to be the G1, which is going to be this tube right here. And I want to measure it with respect to my cathode. And look at that, minus 16 volts. And what did we say that we thought it should be? Ha! I love it when the math works out. Hey, let me bask in the moment here, because this really doesn't happen all the time for me. Usually when I figure something out, it ends up being totally wrong, and then I have to figure out why I was totally wrong. But as you can see, everything is working properly, and the amplifier is powering up how it should. Okay, this is really good. Now, I also said I want to take a measurement across this 10 ohm resistor. And let's look and see what the anode current is, not the screen grid, but the actual anode current. So we're going to do that. And that's going to be, where's our 10 ohm resistor? That would be this one here. So if I go from here to here, trying not to electrocute myself, I have 0.27 volts. So 0.27 divided by 10, and you can see we have about 27 milliamps there. And notice that 27 milliamps is lower than the 60 milliamps or 61 milliamps. So there's a couple milliamps missing, right? Because we really wanted 30 milliamps on each tube. So let's see what we have across those 300 ohm resistors now. So if I go from my screen grid, which is right here, let's see if we can get in there again without electrocuting myself. And I go to here, I have 0.396 volts, right? So 0.396 divided by 300. So we have about 1.3 milliamps. So right there, you have about 28 or 29 milliamps there. So you can see by measuring this, your screen grid voltage is low. It's the way it should be, or your screen current, I'm sorry, is very low. And then you have your anode current, and then those join together with the other tube. And the other tube's probably a little bit different than this one because the windings are a little bit different. And then that should, that will all add up to our 61 milliamps or 60 milliamps, whatever it's sitting at. It all adds up. And you can see over here we have 0.41 volts. We divide that by 300 ohms and 1.3 milliamps, again about almost 1.4 milliamps on the screen grid on this side. And if we look at the actual anode, which is over here, let's see if we can find it right there. We look at it across our anode resistor, the 10 ohm. We have 0.332, so 0.332 divided by 10, and you can see this side is 33 milliamps. So the tubes are not perfectly balanced. So we had about 27 milliamps on one side, 33 milliamps on the other. And I'll show you why that is here in a second. Now the idle current is going to be a little bit different, even if the tubes are somewhat matched, simply because of the DC resistance of this coil. Remember, if I measure from here to here, I will get one resistance. If I measure from here to here, I'll get another resistance. And those resistances will not be exactly the same. Bigger transformers will have a bigger difference between these windings. I don't know what this one's like, but we're set to ohms and we're going to measure it. So I'm going to measure from here to the blue winding, and I'm going to use the one that's not connected to anything. We're going to use the other channel that's not built yet. So if I go from this red to the blue and measure how many ohms it is, everything's unplugged and discharged, by the way, I have about 155 ohms there, roughly. 154.7. So let's just call that 155. So I'll write that down here, 155 ohms. And if I measure this side, it's about 153.8, so it's close to 154. So these ones are pretty close. 154, let's call it. So that's pretty good. Normally there's a lot bigger difference than that. So these are good transformers, believe it or not, so far. Now, why do you think the resistance is different on this side than this side? And why do you think I say that some transformers, it's a pretty, it could be 10 ohms difference between these two sides? Well, in order to do that, we're going to look at a roll of tape. What, Tony? All right. Look at this roll of tape for a second. And let's just suppose that this roll of tape represents that winding around this transformer. See, here's the core of the transformer. You can actually see the windings in this one. Okay? So, if this tape, where it starts in here, represents the blue wire, and this piece of tape on this end is the yellow wire, and about halfway in the middle is our center tap. What do you think is happening here? So if we take the actual circumference here of this first winding, it's going to be shorter than the circumference of this outside winding, isn't it? And remember, the resistance of the wire is based on the length of the wire, because that wire has so many ohms per foot, or so many ohms per meter. And so the inside windings from the, for instance, from the blue to the red, is going to be physically shorter than from the center tap to the outside winding, or the yellow wire. And because this has a longer length of wire, now remember, the number of turns is the same. So from a magnetic standpoint, from setting up a magnetic field, they're equal that way. But in the terms of DC resistance, this half of the coil is going to have lower resistance than this half of the coil, because this half of the coil is physically shorter in length. So you're always going to have a little bit of difference. Now the only exception to that would be what's called a bifilar wound transformer. So like the Macintosh transformers are really super high quality, and what they do is they take the two windings and they put them side by side and wind them around there. So what they would do there, just imagine if I split this in half and I put them side by side, and this would be the one, and I would take, if I split this like this, I would take this end and I would connect it to the inner end of this side. So that would be your center tap, and then this would be the yellow wire, and then the one on the opposite side would be the blue wire. They would both be the exact same winding length, and they would be positioned exactly the same way over the core. So it's going to be a much more balanced transformer than the ones that are wound on top of one another. Now, I do not think this is a bifilar wound transformer, but there you have it. And what that affects is if you have too much resistance difference, you will have a little slightly different idle current on one tube than you will on the other if the two tubes are perfectly matched. So if they're unmatched, sometimes it helps for them to be a little unmatched. Swap them around and you'll find that your idle current will be very, very close. So there's a little tip for you. Okay, I know we all want to see this. So I have a janky connection here of my signal generator into the input capacitors, which is here and here. And I'm just driving it straight in from the signal generator into here. And we're going to see if we get an output. I have an 8 ohm resistor across here, and then I have the oscilloscope connected to that. So we're just going to see if we drive just a 1 kilohertz sine wave in there, what kind of output we're going to get at the speaker terminals. So there's our little resistor connected to the speaker terminals, going through the probe up to the scope. And I'll zoom you into that. Hi. And let's put a 5 volt RMS signal in. And you can see we get a nice output. Now, it's pretty distorted. You notice how the tops are kind of pointy and the bottoms half of the waveform is kind of curved. And this is because we don't have the proper impedance matching, nor do we have any global negative feedback. And the feedback is what's going to clean that signal right up. Remember, this is just a raw output section with not the correct driver section and nothing. We're just seeing if it'll pass the signal, and as you could see, it did. And let's turn it back on for a minute. And let's see if we can capture this waveform here. So we're going to turn it back on as the amp warms up a little bit. And I'm going to stop the signal once she peaks out a little bit there. Okay, and I'm going to shut everything back off. And if we look, we're at 1 volt per division, so I have approximately 1, 2, 3 volts. If we look at the RMS, it's about 1.92 volts RMS. So if we just measure our wattage, I mean, it's low power right now, but 1.92 squared divided by 8 is about a half a watt. So we have about a half a watt of power right now. 0.46 watts. So again, we're not driving this really hard. And my signal generator is not capable of driving the voltages that I need to get full power, but you get the idea. The amplifier works. Now again, we just put a few volts RMS. The drive signal coming out of our driver section and phase splitter is going to be much higher than that. It's going to be capable of going a lot higher voltage. So we're not going to be able to drive the stage properly or anything, but we don't care. We just wanted to see if it passed the signal, and it did. And remember, the output section of an amplifier is not going to have much, if any, gain. It's the purpose of the output stage is not to amplify the signal anymore, but really to provide the amount of current that you need for that amplitude or that amplified signal to go into that low impedance load. Remember, in order to have this kind of voltage across here to get 10 watts or whatever we need to have the proper amount of current. And I showed you that earlier in that little table that I drew in the previous video. So this is not here to amplify. This is here to to provide the amount of current at that voltage level that we need. This back here is what actually increases the amplitude of that signal, and then this splits it off into two opposing signals, positive and negative. This is your phase inverter. This type of phase inverter, the cathodiene, doesn't really have much, if any, gain if it's properly designed. So really all your gain takes place right here, and that's why they're using this pentode right here. And this is not going to be a real high gain amplifier. It's not designed to plug your guitar into it. It's designed for a line level signal to go into it, and it just amplifies it enough to get it to the voltage level it needs here so that we can drive the tube, or drive the speaker. All right, that's as far as we're going to take this video, and I was going to do a clip-on section on the end of this, building this second half, but what I think I'll do is I'll carve that into another part, and we'll just sit down and go over some techniques for assembling this. And while we do that, we'll do a little solder and talk, because I know some of you like that. And once we do that, we'll be ready to move on to the phase inverter section of the amp after that. So anyway, I hope you enjoyed this part. This was a lot of fun. I was really excited to see it work the way right out of the box without any mistakes. So until next time, I wish you all peace, joy, happiness, and good health in your lives. And I look forward to seeing you again real soon in the next part. Until then, stay well and take care, and we'll see you again. Bye-bye.